The polar plots, they are used in the frequency response analysis of control systems. So let us say that what is a polar plot? So polar plot, it is of a sinusoidal transfer function, and this transfer function is G J omega, and it is a plot of the magnitude versus the phase angle on the polar coordinates as omega, that is the frequency. It is varied from 0 to infinity. Now, as we know that the transfer function of a control system, it is given by T is, it is the ratio of the Laplace transform of the output and the input, that is CS by RS. Okay, C is the output and RS it is the input. S it denotes that it is in the Laplace transformation form. Now, if we take the closed loop transfer function of a system, then it is given by Gs upon 1 plus Gs Hs. Okay, this is the closed loop transfer function of a system. Now, in this, if we take the open loop transfer function, then open loop transfer function will be GSHS. Okay, and if we are having a unity feedback system, so for unity feedback system, this Hs, it will be equals to 1. So the open loop transfer function, it will become Gs only, because Hs is 1, so it is going to be Gs only. So the open loop transfer function is Gs. Now here S, it is a complex, so we can denote it as sigma plus j omega. Sigma, it is the real part, and j omega, it is the imaginary part. So S, it can be replaced. S, which denotes the Laplace transform. So if we take the Fourier transform and express it in the Fourier transform form, then S is replaced by j omega. So Gs will become Gj omega. So Gj omega is what? It is the open loop transfer function of the system. So this open loop transfer function, if we take the magnitude of it, then magnitude will be denoted by the absolute form. We will neglect the sign here, and the magnitude is represented by this Gj omega. Okay, and phase angle, it will be denoted by this angle and Gj omega. So polar plot is what? We are plotting the magnitude and the phase angle of this open loop transfer function of the system, and we are plotting these magnitude and phase angle on the polar coordinates, and we are varying the frequency of the system from 0 to infinity. Okay, so once again, let's summarize that what is the polar plot. Polar plot of a sinusoidal transfer function, it is a plot of the magnitude versus the phase angle, and on the polar coordinates as omega, that is the frequency, it is varied from 0 to infinity. So polar plot is what? The plot of both magnitude is represented as this magnitude of Gj omega, and phase angle, make an angle sign and then Gj omega as a function of omega. Okay, so the polar plot will be Gj omega versus this angle, phase angle, as omega is varied from 0 to infinity. So this is a polar plot. We are plotting both the magnitude and phase angle on the polar coordinates, and we are varying the frequency from 0 to infinity. So this was the basic definition of the polar plot, that what we do in a when we plot a polar plot for a system. Now how we can use this polar plot to find out the stability of the system, closed loop stability. So for closed loop stability, the open loop transfer function it becomes GSHS. If we want to find out the closed loop stability, the open loop transfer function becomes GSHS, and instead of GS. Okay. So open loop transfer function, it is generally GS, but if we want to find out the closed loop stability, it is GSHS. Now if HS is given to as 1, that is a unity feedback system, then HS will be equals to 1. Otherwise, GS is considered as the open loop transfer function. Okay. So here we are finding the closed loop stability, because always for closed loop stability we use the open loop transfer function GSHS. Okay, and here HS is equals to 1, so we will take this GS because it is, if in the question it is not given that HS is 1 or any value of HS is given, you have to take it as unity feedback system and you have to consider this GS as the open loop transfer function, and using this you will find out the closed loop stability by the polar plots. Okay, now the polar plots, what are the basics of these polar plots? The first basic point is that in polar plots, the magnitude because we have said that in the polar plots what we do, we plot the magnitude and the phase angle. Okay, so in polar plot the magnitude is plotted as the distance from the origin while the phase angle is measured from the real axis. So in polar plots, the magnitude is plotted as the distance from the origin, while the phase angle it is measured from the real axis. So this is a polar plot. This is imaginary axis. It is real axis. So the distance from the origin, it is the magnitude, and phase angle, we are going to measure the phase angle from the real axis. Okay, this is phase angle. Okay, this was the first point which you have to keep in mind for the polar plots. The second point is that in polar plots, the magnitude, we have said that it is the distance from the origin. So the polar graph sheet, because we are plotting the magnitude and phase angle on the polar coordinates. So we will be having a polar graph sheet, and this polar graph sheet has concentric circles and radial lines. So polar plot of a system, it will consist of concentric circles and radial lines. Now what these concentric circles and radial lines they represent? Concentric circles, they represent the magnitude, and radial lines represents the phase angle. So polar plot, it will consist of concentric circles and phase and radial lines. Concentric circles means the magnitude, and the radial lines they represents the phase angles. Okay. Now in polar plots, a positive angle means if we are getting a positive phase angle, then this positive phase angle it is measured anti-clockwise, whereas a negative phase angle is measured clockwise. So whenever we are getting a positive phase angle, we will measure it anti-clockwise in this, and whenever we get a negative phase angle, it will be measured clockwise. Okay, so this is how we measured a positive and the negative phase angle in polar plots. Next, we have that the polar plots is used to find out So we are using the polar plots to find the stability of a closed loop system from its open loop transfer function. So polar plots can be used to find out the stability by the through the open loop transfer function. So these are the basics of the polar plots which you have to keep in mind. Next, What are the advantages and the disadvantages of the polar plot? So advantage of polar plot is that it gives the frequency response, characteristics, so polar plot, it is the plot of the magnitude and phase angle as we are varying the frequency from 0 to infinity. So what this polar plot is giving, it is giving us the frequency response characteristics of the system over the entire frequency range, that is starting from 0 till infinity. It is showing us that what is the characteristic of the system as the frequency is changing, and on a single plot we are getting the entire frequency range from 0 to infinity. So it is the advantage of this polar plot. Now the disadvantage or the drawback of polar plot is that it does not give information about the So the polar plot, it does not give information about the contributions of each individual factor of the open loop transfer function. We take the open loop transfer function, we take its magnitude and phase angle, we plot the magnitude and phase angle over the frequency range, but it doesn't give us information that each individual factor which is contained in the open loop transfer function, what is the contribution of that factor, that is what the gain is contributing, what the power of S and the factors of the S poles, zeros, what is the contribution of these individual factors in the frequency response of a system. So this is the drawback of the polar plots. So we have studied the advantage and the drawbacks, we have studied the basics of the polar plot. Now let us see that how we can draw the polar plot of a system. What is the procedure to plot the polar plots? Okay, so let's just see that what are the steps which we have to follow to plot the polar plots. The first step, or we can say the method, first way is to the express the given expression of open loop transfer function in 1 plus st form. Okay, we are given the open loop transfer function, we will use the open loop transfer function to plot the polar plots. So the open loop transfer function, you have to express that expression in 1 plus st form. Whatever form it is given, change it in 1 plus st form. So our first step will be this. Now second step will be to substitute this S by j omega. So we have to substitute this S by j omega in the expression for GS, HS, get G, J omega, H, J omega. Okay. So first step was we are given the open loop transfer function. We have to convert it into the form 1 plus st. Then we have to substitute the s by j omega and we have to obtain the expression for g j omega h j omega. Now third step is to get the expression for the magnitude of g j omega and h j omega and the phase angles of g j omega h j omega. We have obtained in the second step g j omega and h j omega. Then in the third step, get the expression for the magnitude and the phase angle of this gs g j omega h j omega, that is the open loop transfer function. Now fourth step is to tabulate the various values of magnitude, phase angle for different values of omega ranging from 0 to infinity. Okay. We have obtained the expression for the magnitude and the phase angle. So in fourth step, we have to take various values of this omega, that is the frequency. We will take different values of omega from 0 to infinity. And for those values, we will find out the values of the magnitude and phase angle and then tabulate it in a table. Okay. So this was our fourth step. Next, fifth step is usually the choice of frequency in fourth step, we have to calculate the values of magnitude and the phase angle for various values of omega from 0 to infinity. So from 0 to infinity, there are many values. So which values we have to choose? So generally the choice of frequency will be the corner frequency and around the corner frequency. Just take those values and for those values calculate the magnitude and the phase angle. Okay. Sixth step is now we have the table having various values of magnitude and phase angle. So in sixth step, we will start plotting the polar plots. So first step will be plotting the polar plot. We have to choose proper scale of the magnitude circles. Because polar plots, it consists of concentric circles and radial lines, and the concentric circles, they represent the magnitude. So for magnitude, choose proper scale according to the table, and next fix all the points So fix all the points in the polar graph sheet and then join the points by a smooth curve. You have the magnitude values in the table. So fix those points and then join these points by a smooth curve. Okay. Then next step is write the frequency corresponding to each of the point of the plot. Now concentric circles on the polar plot, they are representing the magnitude, and according to the phase angles we will draw the radial lines. So these radial lines and the magnitude, they are plotted as a function of the frequency. So we have the smooth curve, we will obtain a smooth curve joining all the points of the magnitude, and on the radial lines which we have got, write the frequency corresponding to each of the point of the plot. Like for suppose omega equals to 0, you have obtained a magnitude value and a phase angle. For magnitude, you have fixed that point, and for phase angle, you have drawn the radial line. So on that radial line, write omega equals to 0. So for omega equals to 0, this is the magnitude and the phase angle of the Gj omega and Hj omega. Now for another, like for omega equals to infinity, omega equals to 1, you have got various radial lines for all those frequencies. So write frequency on the radial lines so that you will be able to get that for this frequency, this is the magnitude and the phase angle of the system. Okay, so this completes the steps of how to plot the polar plot of a system. Let's summarize these points again one by one. First step will be to express the given expression. We are given in the question, we will be given the open loop transfer function. So you have to express the open loop transfer function in the form 1 plus st. Convert it in that form. Now substitute s equals to j omega, that replace this s by j omega in the expression and get gj omega and hj omega. Now get the expression for the magnitude and the phase of this transfer function. Then for various values of omega between 0 to infinity, calculate the magnitude and the phase angle and form a table. Okay, and after forming that table, you have to choose a proper scale for the magnitude and then fix all the points and join these points by a smooth curve and write the frequencies on that radial lines which are representing the phase angle of the system. So these are the steps. Let's take an example so that you will be clear. You will clearly understand that how we can plot the polar plot of a system. Let's take an example. So in our example, we have to sketch the polar plot of the frequency response of the following transfer function, and the transfer function is given as Gs equals to S upon S plus 1. This is the open loop transfer function of the system. Because it is not given to us in the question that the system is having unity feedback or anything, it is not given, so you have to take Gs as the open loop transfer function of the system. Now step number 1. Step number 1 is to write the open loop transfer function of the system in 1 plus st form. Okay, so this is the open loop transfer function GS. We have to write it in 1 plus st form. It is already in 1 plus st form, so this is s upon 1 plus s. Okay, we have written it 1 plus s, so t here it is 1, so we have expressed this open loop transfer function in 1 plus st form. Now step number 2. Step number 2 is to determine the sinusoidal form of this transfer function. Sinusoidal form is obtained by replacing this s by j omega. So put s equals to j omega so that you will be able to find out the sinusoidal form. So g, it will become g j omega, and it is j omega upon 1 plus j omega. Okay, so we have obtained the sinusoidal form, that is g j omega of the system. Now step number 3. Step number 3 is to write the expressions for the magnitude and the phase angle. So Gj omega, it is what? J omega upon 1 plus j omega. Okay, so magnitude will be, that is m, it will be omega upon under root of 1 plus omega square. Okay, so this is the magnitude, and phase angle, that is angle of gj omega, it will be tan inverse omega. Okay, that is numerator, we are taking tan inverse of omega upon 0, and then we have minus tan inverse of omega upon 1. Okay, this is the phase angle. When we solve it, putting the values, we have tan inverse of omega by 0, that is tan inverse of infinity, it will be 90 degrees minus tan inverse of omega. So this is the expression for the magnitude, and this is the expression for the phase angle of the transfer function gj omega. Okay, now step number 4. In step number 4, we have to tabulate the magnitude and the phase angle for various values of omega from 0 to infinity. So using these two equations which we have obtained, for various and omega, it varies from 0 to infinity. Okay, so you have to use these two equations and you have to form a table. So our first value is 0. Okay, we have taken omega as 0. Now magnitude is what? Omega upon under root of 1 minus 1 plus omega square. Put the value of omega here as 0. So 0 upon 1 plus 0. So it will be 1. So our magnitude will be 0 for omega equals to 0. Now here if we put tan inverse of 0, it will be 0. Then 90 degree minus 0, it will be 90. So our phase angle will be 90 degrees. So for omega equals to 0, magnitude is 0 and phase angle is 90 degrees. Now choose another value of frequency omega. Let us suppose we have choose 0.1. Now in the magnitude expression, this equation number 1, put omega equals to 0.1. So 0.1 upon under root of 1 plus 0.1 square. So it is approximately 0.099 and we can approximate as 0.1. Now in the phase angle equation, put omega equals to 0.1 here. Then this angle, it comes out to be approximately 84.3 degrees. Do the calculations and obtain the value of magnitude and phase angle for omega equals to 0.1. Now take another value like 0.3. Put it in the magnitude and phase angle expression. We will get for 0.3, we will have the magnitude as 0.3 and angle as 73 degrees. Similarly, for various values, obtained the magnitude and phase. For 1, if we put here 1, then 1 upon 1, here 1 plus 1 square, that is 2. So it will come out to be 0.71. And phase angle, here we are having tan inverse of 1 here. So this will be 45 degrees. Now next, getting the value of omega here as 1.5. So for this, if we take omega equals to 2, here we are having 0.9 and the phase angle is 27 degrees. Next, if we take another value here, then we are having omega as 5, then 5.0 is 0.98 and 11 degrees. And last, we will take the value as infinity. So if in the magnitude expression we will put omega as infinity, then the magnitude will comes out to be 1 and the phase angle it comes out to be 0 degrees. So we have got the values for the magnitude and the phase angle for different values of omega between the range from 0 to infinity. Okay. Now using this table, now plot the polar plot of the system. So our step number 5 will be to plot the polar plot. We were having our open loop transfer function given to us as s upon s plus 1. Now in the table we were having the various values of omega. So on our this axis we will take various values of omega starting from omega equals to 0 to omega equals to infinity. This is our imaginary axis, this is our real axis. Okay. Now we have to choose a proper scale for the magnitude. So this is 0, Now, for omega equals to 0, we were having magnitude as 0 and the phase angle is 90 degrees. So, magnitude is 0 and phase angle is 90 degrees. We will draw it like this. Okay, this is plus 90 degrees. This is the radial line for the phase angle and this is the point for the magnitude. Okay. Now next we have for omega equals to 0.1, we were having magnitude as 0.1 and the phase angle is 84.3. So magnitude here is 0.1 and the phase angle is 84.3. So we will draw the phase angle here. This is 84.3. Next we have for 0.3 we have magnitude as 0.3 and the phase angle is 73 degrees. So this is 73 degrees. Then we have for omega equals to 1 magnitude is 0.71 and the phase angle is 45 degrees. So 45 degrees will be this. Then we have an angle 34 degrees. Then we have 11 degrees. And then we have 0 degrees angle. Magnitude is 1. Okay. Now write the frequencies on these radial lines. This is for omega equals to 0. This is for omega equals to 0.1. Okay. This is for omega equals to 0.3. This is for omega equals to 1. This is omega equals to 1.5. Omega equals to 5. And this is omega equals to infinity. Plot the points also here. For omega equals to 0.1, we were having the magnitude as 0.1 here. Zero 0.98 and 1. So join these points. Okay. So by joining these points, we have obtained a smooth curve, and on the radial lines we have written the frequencies. This is omega equals to 0, this is omega equals to infinity. So this is the polar plot of the system. We have plotted the magnitude and the phase angles as with respect to the omega, and omega is varying from 0 to infinity. So this is how we plot the polar plot of a system, okay, using the following steps. Now let us see that what will be the polar plot for the various types of transfer functions. There are standard transfer functions. So let's take a tabular form and then we will see that if the transfer function is in this form, then what will be the polar plot. So let us study the polar plots for some typical transfer functions. Okay. Now first we have take the form when the transfer function is in the form 1 upon st plus 1. If the transfer function given to you in the question, it is of this form 1 upon st plus 1, then its polar plot will be this is our imaginary axis, this is real axis. This is the omega equals to 0 and it is omega equals to infinity, and its direction will be like this. So it is the polar plot when the transfer function is in the form 1 upon st plus 1. Second form is when transfer function given to you is in st upon 1 plus st form. Then polar plot will be like this. It will be omega equals to 0 and it will go towards omega equals to infinity when the transfer function is in the form st upon 1 plus st. Third, we have transfer function is in the form 1 upon 1 plus st1, 1 plus st2. Just remember these, that how will be, what will be the shape of the polar plot. So if you see in the question that your transfer function is in this form, is of this form, then you can get an idea that the shape of the polar plot will be like this. So just remember these few standard forms so that you will be able to get an idea that what will be the shape of the polar plot. So if the transfer function is in this form, the polar plot will be like this. Now next we have the fourth form of the transfer function, that is gs is equals to 1 upon 1 plus st1. So in this case the polar plot will be like you can see that if we are adding the poles in the transfer function, then this polar plot, it is moving the quadrants, that is first it is covering the third and fourth quadrant, now it is also covering the second quadrant. So this is the effect of adding the poles in the transfer function. Fifth transfer function is of the form gs equals to 1 upon s 1 plus st1, 1 plus st2. That is, if we are having a pole at the origin, then what will be the polar plot? The polar plot will be like this. It is omega equals to 0. Okay. Sixth, we have, if we have only one pole and this pole is at origin, that is 1 by s, then the polar plot will be the imaginary axis. This is omega equals to infinity and it is omega equals to 0. So this is the effect of again adding the poles, and one pole is at origin, then this is like the polar plot will be like this. If we are adding two poles, then this will be, it will shift towards the left hand side. Okay. Next we have the seventh form of the transfer function, that is gs equals to 1 upon s 1 plus st1. One pole at the origin and another pole at t1. Then the polar plot will be like this. Eighth, we have transfer function. We have 1, 0 and then one pole at origin and two other poles. We are having a 0 also in this case. So the polar plot will be like this is omega equals to 0. It is omega equals to infinity. Next we have if the transfer function is given to us in this form, then its polar plot will be like this. This is omega equals to infinity, omega equals to 0, imaginary axis, and this is real x. Then we have transfer function of the form 1 upon s squared, that is two poles on the origin and two other poles also. Then the polar plot will be like so. These are the 10 transfer functions. These are the typical transfer functions for which we have got the polar plot. So whenever we have any question to sketch the polar plot of a system, we will see that what form of the transfer function we are having, and then we have an idea that its polar plot will be like this. So we can compare the transfer function with these standard transfer functions and have their polar plots. So in this video we have studied about the polar plots which are used to obtain the frequency response analysis of control systems. Okay, then we studied the steps how we can plot the polar plot using an example also we have seen, and then we see some standard typical transfer functions for which we have obtained the polar plots. So I hope this video is clear to you. Thank you.